I'd like to go ahead and get started, if we could. So it's my pleasure to introduce Yin Wang, standing right over here. So Yin, we've actually known him for many years. He was a graduate student at University of Michigan, working with Stéphane Lafortune, who was a graduate student here while I was a graduate student here. So I guess that makes Yin a grand student of Berkeley. But he graduated with his PhD in 2008, did a very elegant thesis on the use of synthesizing control algorithms to prevent bugs in concurrent software. So it was a very innovative combination, multidisciplinary kind of application of some pretty sophisticated techniques. Very, very nice work. And Yin has been at HP Labs ever since and is currently focused on big data systems with a particular focus on geospatial kinds of applications. So that's what Yin is going to be talking about today. So I'll turn it over to him. Thank you.
Thank you so much. Thanks for the introduction. Yes, I did some work in control theory. I had a background in control theory. I like it very much. This is somehow it's totally different from control theory because we are in Silicon Valley. You know, everything changes every 5 years, right? I still love control theory. I still want to do something about it. But at this moment, I want to know more about this new sort of big data crisis and to see what we can do about it. And it happens to be well aligned with this new swarm intelligence kind of a project. And that's why I think it's a good synergy, and that's why I'm here. And hopefully I can get great comments and feedback from you guys. So we all know about big data. There's a common sort of sense on like 5 V's of big data. Volume, obviously, is a big thing. It's too large to fit in one computer. Velocity is also very important. Means that the data comes at the speed, and you have to be able to process them. And for our case, at least for what I'm going to talk about today, velocity is more important than volume. And there's also a variety, which means that you are having data from different sources and have different formats and different basically different inputs, right, from different sensors. And then veracity means that data has a lot of problems. You have to be able to correct them or make sure it doesn't affect your analysis. And value is the most important thing. Without value, if you don't want to extract any value from a big data, you know, big data is just a buzzword. Then there are lots of sources of big data. In this talk, I'm just going to talk about geographic information system, mostly because this is where we get the sources, and at one point, HP was very, very interested in this kind of area. So in terms of GIS data, there are lots of GIS data around us, right? There's traffic data. Berkeley has done a lot of analysis on this loop detector data, dating back to 60s and 70s, I believe. And now there's some new, like San Francisco is installing new parking meter. It's all internet connected. Right? Traffic lights are also wired. In the city of San Jose, all the traffic lights are wired. You can control it in one control room. And people are actually doing something about it. And then there's vehicle data from telematic systems. Those are very advanced sort of data. Not only you get the location for the vehicle, you also get the engine information. Do I need any fuel? What I'm carrying, and my destination, or you know, all those schedule. Everything is all inside this one truck. And then photo, video. This is where the volume comes in. If you worry about the volume, there's also volume in this GIS data area. And smartphones are also increasingly abundant, and with lots of sensing data as well as location data. And then for us, what we're interested at the beginning is that because HP is an IT company, right, we have a lot of customers, and many of them are interested in GIS applications, including governments and transportation agencies. And we are thinking about building a platform to gather all this kind of data and support different needs, right? And that was the purpose. So that's the background. I'll talk about a series of work we did in the past 2 years, mainly focusing on GPS data, and then I'll talk a little bit about this platform I just introduced. So we gathered lots of GPS data from China because there are just so many taxis out there, and it's easy to get the data because they typically manage those data in one source, right? There's like a phone call dispatching company. They try to gather all those taxi data in one source. And those governments, they also try to gather the data in one source so they can regulate this industry. So we have tens of thousands of taxis for up to 2 years. In Shanghai, we have 2 years. There are lots of information there, latitude, longitude, obviously, timestamp, and speed and bearing, and all those status information also there. And then this is what it looks like, right? If you plot it on Beijing map, this is what it looks like. This is only 2 hours of data, by the way. And then for Shanghai, this is again, I think it's probably 4 hours of data in Shanghai with all those trajectories. And the first thing we did once we get the data, we want to know what's in there, right? So we did some statistics and just to see what's happening. The most interesting thing you can see is the interval, which means the sampling interval, right? We just plotted this histogram of all those data. And you can see this is not a uniform distribution. It's not like, 1 minute interval or fixed number. It's just lots of different settings. It's because it's a big database. They gather everything from different taxi companies. Every taxi company has a different setting. And actually, every taxi has a different setting. Even for one taxi, they have different sampling interval when the taxi is vacant versus the taxi is occupied, right? So in some cases, for example, this kind of sampling intervals when it's beyond 5 minutes, it's probably not that interesting. But with this amount of data, even if you just focus on taxis of sampling interval below 60 seconds, below 1 minute, you still have lots of data out there, right? So it depends on how you use it, but you have to be aware all those things have a lot of variation there. And also for speed, you can see it never stops at like 160 kilometers per hour, right? It goes all the way to whatever is allowed in the database because all those data issues and also all those sensor inaccuracies. By the way, feel free to ask questions if you have any, because I think the setting is great. It's kind of informal, and then I want to exchange ideas. And Veracity, we were talking about Veracity. This is just some examples of kind of error you can get from the data. In that one case, the taxi goes to the sea and comes back, right? It's not possible. And here is more like a normal kind of noise when you are in a city canyon. You basically just have lots of data that's sort of drifting around. It's not super fast, so if you use a speed kind of detector to remove outliers, you won't be able to filter out this kind of noise. You have to be smarter about it. And here is just tunnel. When you have a tunnel, you don't get any signal, and it keeps reporting the previous location until it reestablishes the signal and calculates the new location. So you have to know this is not a road. This is actually the taxi was just calculating. How do you get this? This is all important. And not only about the GPS data can be wrong, you can also get maps that are wrong. These are Bing aerial imagery, right? This is from Microsoft. And you can see it's not aligned with the map. At the beginning, I thought it's probably some GPS data problem, but eventually I realized this has to be the map itself. Probably because of distortion or because of some other problems. They didn't get it right. So that's the data part. We believe the large-scale GPS data are increasingly abundant. I only got the data from taxi companies, but if you go to Google, go to Apple, everyone has lots of data from all your cell phones, right? And then the data has a lot of issues. We have to rely on advanced techniques like the robust statistics or large quantity to help mitigate those issues. So that's the data analysis, basic kind of study just to gather what's inside the data. And then we did 2 kinds of data mining applications. So first I'm going to talk about map matching. So map matching, basically you have sequences of GPS coordinates. Every GPS sample is essentially a latitude-longitude pair, right? Once you have the sequence, the first step is to find the most likely route on map where the taxi is probably taken, right? And you can see from this case, this is a non-trivial problem. You may have a sequence of coordinates. You have to look at them as a whole to figure out, oh, the taxi was actually driving along the ramp, not on any freeway, right? And we studied the literature a lot of, there are just tons of algorithms out there in computer science, in civil engineering, in many, many different communities. People have studied this problem. And we find that everyone has the same kind of strategy to do this. Basically, for every time you have a sample, you just draw error circle because we assume GPS follows standard Gaussian distribution. So you draw an error circle with like 95% standard deviation or 95% of probability with the sample being inside the circle. And you draw all of them. And every circle includes lots of roads. These are sort of candidates for this sample, right? So this sample has to match to one of those roads, right? So those are candidates, and every circle has also candidates. Now the next step is to get one candidate road from one error circle and link them to build a trace. Now different methods differ in the way they pick the candidates, right? They use lots of different criteria. So we did some summary. You have lots of algorithms out there, and then those columns are different sort of features people use to select the best sequence of candidates. So for example, distance means that the distance between a sample and a road. The closer it is, it means more likely the taxi was located on that road, right? And more interesting features are like shortest path, which means for two consecutive samples, you have many choices of roads for each one of them. And when you pick two of them, you have to worry about the shortest path between those two roads. If it's a long detour, then it's highly unlikely that's a route taken by a taxi. If it's a straight road, then it's more likely that's the case. So this naturally maps to, if you're familiar with the hidden Markov model, the distance naturally matches to emission probability, and shortest path naturally matches to transition probability. And that's exactly what people use. In summary, there are two categories of methods. One is called incremental online. In this case, when I want to determine the current location of a sample, I just look at the history, look at past history, look at the samples around me. This is needed when you are doing sort of real-time navigation. When you're using your GPS devices, it has to be online, right? It cannot tell you the current location like 10 seconds from now. And then global offline is when you can look at the whole trace. When I give you a trace as a static, data source, and you can try to find the most likely route for it. Now we did some comparison of all these different methods. We can see that global offline algorithm performs much better than incremental ones. Incremental ones are only like 90%, and the global offlines can go as high as 99%. Of course, as the sample interval increases, all those accuracy decreases because you're just too long, and it's difficult to figure out the route you've taken in between. And why this is the case? So this is why those local algorithms perform very poor, right? You guys will have all experienced this with your own GPS device. When you're taking a ramp on freeway, or you didn't take a ramp on freeway, it says, oh, you're on this ramp, until you're just too far from the ramp and you realize, oh, you're not at the ramp. So now it has to recalculate your route, right? This is exactly what happens. Because of noise or because of inaccuracy of the map, your samples happen to align with the ramp a little bit closer than the main freeway. So you thought it's on that ramp. And because it's local, it cannot look into the future to figure out what's happening. So it has to wait until it's too far. It's outside of the error circle and decided, oh, this is not the route you've taken. So this is why incremental algorithms are not good. And global algorithms, as I mentioned, the hidden Markov model is exactly sort of best performer in our experiments. And we just did a little bit of tuning about those models, just tune the emission probability and the transition probability a little bit better to account for dynamic sampling rates. And this happens to be the most accurate, one of the most accurate algorithms.
Is the idea that dynamic sampling rates that you might want to sample more when there's acceleration?
Dynamic sampling rates means that for even one trace, you have different sampling rates.
Yeah, it seems to me you may want to increase the sampling rate when the car turns.
Yeah, that would be nice, right? In our traces, we have dynamic sampling rates because taxis can take samples at various moments. For example, as I said, vacant versus occupied have different sampling rates. And when status changes, like they have a customer on board, they will send a sample. So we have no control over it.
But do they change the sampling rates based on any accelerations of the...
No, because that sampling is only for phone call dispatching. They want to know the location of the taxi. So for that purpose, they're not really worried about that. But we actually did something like that later. I'll talk about that in some of our later applications.
You would think you could save on processing load, processing overhead by switching on and off the error circles based on the GPS coordinates. In other words, certain areas would require it and certain areas would not require it.
Well, yeah, that's a very excellent point. Actually, you can do even better than that because if you're programming your navigation software or your fleet management system yourself, you have more information on the accuracy than just plain traces we get from taxi companies. Because, for example, Android and everything, they have this API called get accuracy function. I assume it's determined by the satellite signal strength and how many satellites you have, information like that. So you can use that to determine your location, and you can actually increase the map matching speed. If you know it's a small error circle, then it's a lot faster. Yes, that's very important. And we actually, one of our applications will use that feature later on. So this is some experiments we did, and we also, just to sort of convince ourselves we did the right thing, we also collected some high noise traces in Shanghai, because we find that all those so data sets in the literature, they're all sort of controlled experiments. They drive around the campus a little bit and get very high quality data, and it's very little interest, right? When we show the sort of accuracy is always 99% for those global algorithms. So here with more noisy data, and if you decrease the sampling interval, we get a lot worse performance. But it's still more than 90%, and that's the reason we believe our algorithms are very good, and that enables us for our other applications. So as a summary, I told you that incremental algorithms are perform poorly, and global algorithms, especially hidden Markov model, are very good. It's up to 90%, at least 90% accurate, up to even 1 minute sampling interval. This means that for large amount of data out there, which are sampled at a very low sampling interval, this can still be useful. And then we find that map accuracy is one of the major sources for map matching errors. When something wrong happens, we find that in many cases it's that the map is wrong, not our algorithm was wrong. Right? And this motivates us for the next project, which is map inference. If a map can be wrong, and GPS are much better in that sense, then can we infer the map from GPS data? So in this area, there's also, similar to map matching, there's also a lot of interest. Many people have done that, and we summarize everything into sort of 3 categories. Also 3, so well-known data mining algorithms: k-means, kernel density estimation, and then clustering, right? So I'll talk a little bit about that. So k-means clustering, this is what it does. You have lots of raw GPS traces, and they want to distribute the seed along those traces. They want to guarantee that every seed is at least d distance apart, right? Once you have those seeds, you run the k-mean clustering, and you find a better location of those seeds, which are typically centered around a big mass of GPS samples. Once you have that, you look at the trace and try to link them to build the road. If you see a trace whose previous sample is inside one cluster and another one is inside another cluster, you just link a line to it. But this algorithm performs very poorly when you have very sparse data, when your sampling interval is too long, because samples can jump one seed to another location, right? Because it's long sampling interval. So it doesn't even work when the sampling interval is beyond, say, 10 seconds. So we didn't include this in the performance study because it's not so interesting. Kernel density estimation is much more interesting. Once you have lots of samples, you don't even have to look at the trace. You just draw those samples as a density map on this 3D surface, and you can see that more samples you have, then you have higher sort of mountains, right? Those mountains are essentially, in this case, those bright areas are actually the freeway of Shanghai, and those light areas are more like residential roads. Now, once you have this density map, if you can somehow extract the ridges of those mountains, those are your roads, right? That's essentially the basic idea. Of course, because of the data disparity and all those, residential roads versus freeway, you have to do a lot of engineering to make sure we get the right roads, but that is essentially the idea. So for us, we developed a slightly different algorithm. We use clustering to do that. So you have lots of GPS traces at the beginning, and then first we do some cleaning, because when the sample interval is too long, we want to break them down, right? If you have a short period of high sampling frequency data, and then we developed a slightly different algorithm. We use clustering to do that. So you have lots of GPS traces at the beginning, and then first we do some cleaning, because when the sample interval is too long, we want to break them down, right? If you have a short period of high sampling frequency data, and then we developed a slightly different algorithm. We use clustering to do that. So you have lots of GPS traces at the beginning, and then first we do some cleaning, because when the sample period of high sampling frequency data, and then we developed a slightly different algorithm. We use clustering to do those, and they have a similar bearing. That's more likely like from one road, and you do a spline fitting, you get some road like this. So this is also very interesting, and we did some visual comparison, and this is what it looks like, right? To know more about the sort of quantitative evaluation of different algorithms, we use this sort of common evaluation matrix, which is the F measure, right? We have precision and recall. By precision, we mean for the rows we generated, how close are they with the actual map? in this case, we'll penalize those algorithms that generate spurious traces, spurious roads, because they are just overlapping with existing roads. And recall means for those roads in the map, how many of you can discover by your data, right? So with this kind of two measurements, you can have a more detailed comparison of those two algorithms, and this is what it occurs. Those dashed lines are the isoclines of the F measure. So essentially, you can see for our trace clustering algorithm and KDE, one variation of KDE, it performs very close. Ours are probably slightly better in recall, and theirs are probably slightly better than in precision. And also, we can vary data volume to see how it performs, and also, again, it's very close. And typically, the more data you have, you perform a little bit better. To a certain point, when you have too much data because of noise, neither of these algorithms are very good at filtering out noise effectively. So as a sort of a recap, with large scale data, we believe GPS traces can be more accurate than existing maps. And the KDE and trace clustering algorithms are the top performers. They have a different trade-off between accuracy and coverage. As a limitation, you can definitely imagine road metadata. We cannot infer that from GPS data alone, right? We don't know the name of the roads. We don't know the street numbers of certain roads. And also tunnels and plane-separated roads are also one big limitation. But then this motivates us to the next problem, which is the system we build to update maps. We know maps are already there. It's not accurate. But with GPS data, can we update the maps? Right? This is more interesting than building maps from scratch. Building new maps is sort of interesting from an academic point of view, but in practice, we want to really update maps. And this happens to be a real hot topic these days, right? Because of the recent Apple-Google map war. People are complaining about map accuracy all the time, and in some cases leading to serious accidents. And this is probably more prevalent than our common belief. This is one example I found in San Francisco accidentally. So this is 101 freeway and the Market Street, one of the busiest intersections of San Francisco. It's well known that you cannot turn right to 101 from Market because of cyclists, pedestrians. There's lots of accidents because of people making illegal right turns, 2 of them fatal. Right? But if you go to Bing Map for navigation, this is what it says. Right? You cannot make a right turn, just go ahead and make a U-turn and then take a left turn. Both of those turns are forbidden. Right? And if you love Google, this is what Google says. A month ago, they've changed this once I told them this is a problem. So it says you can go up to Octavia and take a byway and then make a U-turn. But if you look at the street view, this byway is actually a cycling way, right? And that one, even the left turn is forbidden. You cannot really make a U-turn from that. So if you follow their advice, and this is even more dangerous than making a right turn to 101. And actually, there's lots of discussion on who is liable for accidents caused by map errors. So this is very serious. And why is there so many issues with maps? Because everything is done manually these days. Even with all those, 500 years of advance in modern cartography, everything is done manually. Navtech has more than 7,000 people just to get the map right. And in that case, actually, Navtech did it right. I think it's probably because they have more people than other companies do. But that happens to be one case where they did better than Google and Bing. Even though Bing is actually use the same Navtech map, but they did the navigation algorithm on their own, so I guess they messed up some sort of map features. And motivated by all this is what we built. We want to get the data from all those different map sources, from different sources, like fleet management system. I told you there are lots of taxi data around us. And then, Google, Apple, they have all lots of cell phone data. And also, for those people who build GPS for live traffic, they also have data from those systems as well. For example, OnStar has 6 million subscribers around the US, right? If you turn on those GPS navigation from OnStar, they can get your data as well. So once you have the GPS stream, we use this server to continuously update the map. You first go through a map matching process I just described. And this one, we'll separate matched trace segments and unmatched trace segments. Matched trace segments can be used to adjust existing map, right? You see those are matched to the road, but it's some sort of geometry problem or closure. You can use that to adjust existing map. And unmatched trace segments can be used to augment the existing map, right? can be new roads, new sort of intersection, and this is what we do. So just to give you some idea about this, I think I'm just going to talk about different kind of components, right? So for example, one thing you can do is new road detection, right? Here you have road traces, and after map matching, we get rid of all those traces that are already well aligned with the map. When we see the map matching algorithm using hidden Markov model, if you don't see any problem, if the transition probability is not 0, we know it's a good trace. And in some cases, the transition probability can be 0 because of the missing intersection or could be missing road. And then we say that's not matched, right? And we draw those unmatched trace segments as red and well matched as black, and this is what you get. And once you get this, I described this trace clustering algorithm where you can cluster those traces that are very close to each other to form a road, right? And this is what you get below. You can see a lot of noise data there as well. But as long as you don't have 2 or more noise traces that are very close to each other, you don't form a cluster, right? And we also have a sort of threshold for each cluster. As long as you don't have enough data there, you don't form a cluster. That's why we can effectively filter out noise, because noise traces happen all the time. But how likely is that 2 taxis follow the same noise, right? That's very highly unlikely. And then once you have those clusters, you can fit a line and you get a road like this, right? And you can verify this through satellite image. These are well aligned with the actual road that's missing from the map. Any questions? I'm sort of doing a little bit fast, but I think it's okay.
I have a question about one of the limitations you raised, which was not being able to detect, I forgot the term you used, but roads that are not on the same
plane separated, yes.
Why couldn't you detect it? I mean, I would think, if a road is plane separated, then there's no turns.
Yes, but for example, which one is on top of which one, you cannot really do that well unless you have this altitude information from your GPS.
True, but do you care for the purposes of a map which one's on top?
But actually, all those maps have that information when they do that. So it depends on what you want to do. If you don't care, if you just want to, for example, for autonomous vehicle, you don't want to care about the, which one separates which one, connectivity, and probably don't care. And another problem for plane separated roads, in Shanghai, there are lots of elevated roads. I think this is probably some kind of elevated roads, sort of elevated expressway on top of a local way, right? Here, in Chicago, it's all on the same plane, but in many cases, when you have tight space, you have elevated freeway on top of a local way. Now, it's plane separated, and also have a problem is that bad reception underneath those expressways. And for that, we have a huge amount of noise. That's also another problem with plane separated roads. Yes?
So do you think that this kind of thing is accurate enough that if you were to give live updates to the maps in nav systems in cars or something, or would that be way too dangerous?
That's our belief and also ongoing effort, right? But comparing to what's there in the existing system, it's all done manually. So typically, people can submit some error to Google, and Google has to have a moderator there looking at the map, looking at satellite image, and sometimes they have to even drive to a road to see what's at the latest time. Then this is way better, right? At least we can tell you what are the problems in your map. So actually, I'm talking to Google, and they're very interested in this technology because everything is done manually currently. Even if you can just tell them where are the problems to look at, if you have a high false positive rate, it's better than nothing. So we're competing, we're really competing with nothing at this moment, which is great for us. And then if you apply this whole algorithm to this whole area, whole Beijing area, this is what you see, right? This is what I'm talking about. You can look at this map and quickly zoom into problems, to the areas where you see problem. We actually verified all those results. At least 90% of the roads are highly accurate. We don't have to do anything, and we can upload it to OpenStreetMap. For the rest 10%, if you want to fine-tune it, it's much less effort than going through all those manual edit process and looking at each area by yourself, right?
So is this precise enough to figure out how many lanes you have on a different road?
There is research effort on that, but we don't do that here. Right? The research effort is just looking at the standard deviation of a road to see how wide they are. Right? And there is also effort from Microsoft and Google looking at street view to figure out how many lanes are on the street. So that's what I think that's where the hope is. Combining this technology with all the computer vision technology that can automate everything. Here is, I would say, 90% accurate. 90% automated. But for the last 10%, if you can combine images, that would be great. And for closure detection, this is like standard, time series change detection algorithm, right? Here we have to down a lot of engineering effort because our data is different from the. It's just a lot of noise, a lot of issues there. For example, you don't have the same amount of data every day, right? You don't want to say, if you don't have enough data, then there's a problem there. And also for residential roads, you have much less traffic than freeway. For freeway, you can probably detect the closure in, say, 5 minutes. But for residential roads, you may need 1 week to declare closure of a road. So we did a lot of study to make sure we did it right. And in the end, we used 2 years of data in Shanghai to find closures. We only verify long-term closures because those we can verify through news sources or historical Google Earth image. And we were able to verify 90% of those 88 long-term closures we detected. For short-term closure, we don't have enough data to verify those results. And here's sort of one example. I'm just trying to show you something just to see how difficult it is to find this kind of things manually, right? With all those data going around, with all those maps, big maps, how can you find this? You need some algorithms like this to find those problems. And then another issue is geometry refinement, right? In many cases, maps or roads are there, but people did it wrong, or people use wrong satellite image. I showed you at the beginning. The maps can be, misaligned. The satellite image can be misaligned with the actual map, and people often draw maps from satellite image. Now you can use GIS data to correct those manual drawing, right? And here we have lots of roads, but then for most of them we don't have enough data. And then for the rest 6,000 roads, we can draw this kind of histogram, and you can see most of the roads. Essentially, this is sort of the median location shift, right? We have samples matched to one road, and we find the median location of those samples and see how far they are from this road. That's why it's assigned value, right? It could be left, it could be right. We have defined which one is right, which way is left. And you can see most of them within 15 meters. And we find that within 50 meters, it's difficult to determine which one is wrong. Is the data is wrong or the map is wrong? Because 15 is just so small to verify. So we decided to use 15 meters as a threshold. And then for those cases, when the shift is beyond 15 meters, these are the results. So parallel roads, this is what you mentioned about the lanes, right? Parallel roads, that's a significant problem. Sometimes it's lanes, sometimes if you see the map, it's drawn as different polylines. When you have a very big road, it's typically two opposite direction polylines, which means it's a lot wider than the typical one polyline, right? So if people are lazy, they didn't draw two polylines and as one, you just draw one polyline, and then you may detect some error there. Also, noise is also one issue. We don't have enough data, and if those data happens to be noisy and happen to shift toward one direction, we were not able to find them right. And also because our data is out, there are cases when we detect some error, but those are temporary roads, right? In the latest map is already corrected. So the map error, the true map error we found is only 2, right? And this is one of them. So this is also interesting. For those almost 30,000 roads out there, we can quickly pinpoint down to 2 roads and correct them, right? This is very valuable. And also we're concerned about scalability, right? And we did some base study, and it turns out that map matching is a major limitation, computation limitation for all those calculations. That's why we try to parallelize it, right? I showed you here, right? For map matching is parallel. Everything else is just one single node because you don't have those many updates every day, right? So we try to parallelize it, and it's almost linear scaling because it's essentially embarrassingly parallel, right? Everything can be done by its own as long as you send the trace from one taxi to one server, and you don't care about the rest. But then, because we update the maps, and for the efficient calculation, we have to cache the map in memory because you want to calculate the shortest path. You don't want to do that in a database, right? Using a SQL query to do the shortest path calculation in database is terrible. So we have to cache the map in memory. But then, once you update the map, how do you go and update the cache? There's a significant delay between you map match and then you separate trace and then do all those calculations, right? So you have to use map versioning. When I see a trace from the map matcher and the version is older than my latest map, I have to rematch it to the latest map just to not generate the same road twice. And the last part of the system is a CrowdAtlas app, right? This is Mobile conference. They love apps, and we built one. And actually, this is very useful. Why? Because there are three important reasons for us to do that. First is to build personalized maps. In many cases, people don't want to share the map with others. I have some private roads, or may have my favorite off-road driving roads in a park, right? I don't want to tell people about it. And sometimes I want to build a community map, like cycling map, right? And it's a huge issue for even Google because they don't have enough people to go around and map those cycling maps. Another is a dynamic sampling rate. I mentioned about this dynamic sampling rate. We use that so we can increase the sampling rate when it's mismatched, right? And we have better quality map. When it's well matched, we don't care about that. We can, decrease the sampling rate. However, it turns out that this doesn't save battery for the current cell phones because they have to turn the GPS on all the time. They have to have long duty cycles for them to turn it off. We have to be like more than a minute or so for the GPS to shut down its signal. So, but if it's more than 1 minute, it's probably a very bad experience for the user, right? You have to know my current location. If you don't know, how do I navigate? So, but at least it saves the communication, the data communication to the server. The last is get accuracy information. We can use that to know better about noise versus the real missing road, right? And if you use that app, this is what you feel. You can drive on the road, and if you're driving on the road that's missing from the map, it shows as red. And once you rematch the data to the road, it asks you to confirm this new road. We need the user confirmation because we don't have enough data. It's a personal mode. It's standalone mode. It's not even connected to the internet, right? We don't have aggregated trace data from different users to filter out noise. So we have to ask users to confirm it. Of course, you can turn this off if you are driving off-road and you think it's too sort of annoying. And then if you use this feature, you can generate sort of a block of roads in an area quickly. We did this. This is like 4.5 kilometer square street block, and we did it in only 27 minutes. And in comparison, Google Maps is missing one major road there. If you wait until Google Maps to update the road, that map, I don't know how long it takes, right? They have their own updated cycles. They have to have people driving around to a particular road to map it out. Another useful feature I mentioned is personalized map, right? For example, I worked with students in Shanghai Jiao Tong University. It's a huge campus, but it's enclosed to motorist traffic. So basically, people rely on walking and cycling to get around, but there's no reliable map, and people ask about directions all the time. And here is a very interesting case. From entrance to library, it's very popular and scenic shortcut. It's not on any map, right? But people use that all the time. So if you can just walk around, and this is the footpath because we set the travel mode to footpath, right? And if you look at the previous case, this was driving. We did this manually, but there are many articles and papers talking about how to automatically detect the travel mode from cell phone sensors. So this can be done automatically as well. But for our case, we did it manually. So if you're walking and you find a new road, you will generate a footpath, right? And then you can save this distance greatly, and it helps people to walk around. And if you compare this to commercial maps, Google definitely doesn't include this because they don't have any walking trail, at least not in China. And Baidu, which is Chinese Google, they do have this road, but they label this as a drive path, right? So you can use it for navigation. You can go, if you're driving a car, you can say, this is the beginning, this is the end. Then they will route you through this path, which is definitely not drivable. So these are the sort of apps. And then in terms of challenges, sorry about this. Yes. So in terms of challenges, sorry about that. So this is the case I mentioned. This is an elevated expressway on top of a local way. because of the huge amount of traffic, I didn't even show you the matched traffic because there's so much. It will overwhelm the whole picture. Right? I only show you the mismatched roads. Just so many of them because of the block signal from those elevated freeway, and also because of the huge amount of data there and the Gaussian distribution. You definitely have more noise. And then if you use any algorithm, it's very easy to pick up those noise as a road. And also in this case, it's very interesting because it happens to be a missing road very close to the freeway. Now, how do you detect those reliably? It's very, very difficult. In our case, we have to tune the threshold parameter to get this, right? So it's not that automated, because if you tune that, you will miss some residential route. It's a trade-off between how large you set for the threshold, right? How do you detect this reliably is very interesting, and we think some sort of density-based clustering algorithm can help. And then, how is this useful? So this is some slides from Google. This is what they are doing. I actually talked to them. I believe they're not doing any fancy GPS-based map inference at this moment, but they did use street image a lot, right? So this is actually a slide from their news article. So they can use image detection techniques to get all those signs and even street numbers in many cases from this whole area. So with all this information, can complement our technology, and we can automate the whole process, right? And in our case, we actually rely on satellite image a lot, because every time we find a new road, we want to confirm, we have to go to the image to find a new road. There are lots of techniques to automatically detect roads from satellite image, but there are several limitations, right? For example, tree canopy covered roads is very difficult to detect, right? But now if you know there's likely a road there, if I can point out to you there's likely a road there, and you just want to see if that road is at the right location, it's a lot easier than just detecting the whole map from the images. So as a summary for this app, we can automatically update the maps using GPS data. We can leverage existing large data set, which is great because it's already around there. It's already there, And in our case, we actually got those data for free, so it's great for us. And then you can use this app to build personalized maps, and it can generate better. If you use it as a data source, it can give you better accuracy of new roads and with less communication. If you use it for personalized road, you don't even need communication to the server. And we think this can revolutionize modern cartography together with computer vision techniques, and reducing this manual map update process we use today, right? So these are the applications I did using this data set. And currently, I'm finally back to our original goal of building a platform. Why we want to do this? Because when we did that, when I showed you this architecture picture, we did it all manually, right? In order to scale our algorithm to global data, we have to figure out, map matching is a bottleneck, and we have to parallelize it. And once you use map, you have to do versioning to make sure you don't have a conflict editing, right? Can we build something where people can add it locally, and you can do those development locally and then scale to global data, right? Because every time when we do those developments, what we do is that we try to program locally. We try to get a map for a specific area, try to get data for a specific area, and then we do all the tuning. But then eventually, how do we scale to global data? We have to re-architect everything, right? Can we do this automatically? In some sense, it's very close to MapReduce, right? When people program MapReduce functions, they don't really care about the scalability. But it has several different issues if you want to use MapReduce. The first is that, obviously, MapReduce is not used for real-time calculation. It's more for batch processing, right? For map update, it's probably not that important. But if you're thinking about traffic view, which is also one function that we can incorporate into our system, then you want to get second-level delay rather than minutes delay. So currently, if you look at those traffic data from PERMs, from Berkeley, there's a 50-minute delay, right? I don't know if they run any algorithm that's sort of batch-oriented, but we can definitely shrink this delay to second level if you use a stream-based processing engine. And also, for this specific application domain, there's lots of things that can be optimized. I know AmpLab here has a project called Spark, where they look at iterative machine learning algorithms and on top of MapReduce, where you can just cache the intermediate data to accelerate the computation, right? That's more for iterative sort of machine learning algorithm. For our case, we have a different feature. In our case, our data is sort of localized. What's happening here doesn't matter with what's happening in New York, right? So we only care about data surrounding us. We don't necessarily have lots of iterations, but once we do something, like when we do those calculations, we want to have our maps cached in memory, right? Can we just cache our local maps in memory? Can we automate that? This is what I'm interested. So as a conclusion, I believe geographic information system is a very interesting application area. We have lots of data around us, and it's touching everyday life. You can make a significant impact by doing some interesting applications. And for me, it's a very interesting sort of adventure from my control theory background, because we did a lot of algorithms, we did mobile computing, and lately I'm interested in platform. There's some sort of component there. For example, if we're talking about load balancing, we are thinking about some control techniques to automatically balance the load and have better stability and guarantees. This is still ongoing research. I'm still working on other GIS applications, and we are working on platform support. So with this, I conclude my talk, and I'd be happy to answer any questions. Yes.
So I'm kind of curious about the taking this to a sort of logical conclusion and automatically updating maps and cars. Is there a danger of now malicious data being added by folks in the system to cause accidents, or that seems like that's an obvious
it could be
concern.
Right. So one way to do this is that when we do this, it's also one reason we use a clustering algorithm versus like kernel density estimation, because we can see each individual trace. Right. When we do the clustering, to figure out how to automate. So when you very stupid. When you do run those algorithms, you do have a way to see those individual traces. And for example, you can say it has to be from 3 different cars, right? This adds more difficulty for people to generate a malicious trace. And you may even say, it has to have 3, maybe from 3 different persons, whatever. I'm just saying there's certain ways to know this. And also, at this moment, even though it's 90% accurate, I wouldn't recommend you just generate it to your map and use it every day, right? You still need some manual review. But if you can combine satellite image, that's even more difficult to fake it, right?
But just as a follow-on, so the sensor data, though, is not necessarily authenticated to be truly from a given cab?
In our case, no, not at all.
So it could be possible for somebody to...
Right, and we actually need that because, if you want to cover every road, including residential road, how many people drive there, right? So yes, we can probably authenticate that, but, that could reduce your data source and could, reduce the usability or coverage of the algorithm. But, what's interesting is that maybe you can use this algorithm to generate sort of a plan for a Google driver to go around for the next day, right? And he can drive around and gather more data. And then you can automate this, and then his data can be automated, and the whole thing can be automated. Except the driving step, because you want to confirm it by yourself.
Questions? All right, let's thank Yin again.
Thank you.